Hey stats folks. So we have been working on constructing confidence intervals, right? We use z-scores in our standard normal distribution if we know the population standard deviation. If we don't know the population standard deviation, we switch to the t-distribution, all right? But now we're going to look at estimating p, the proportion in a binomial distribution. Remember that a binomial distribution has either success or failure as the only options. We have a certain number of trials, we call that n, a certain number of successes, and a probability of success. So let's just do a review problem. Okay. Let's say the probability of winning a carnival game at the county fair is 25%. If you play the game 5 times, what's the probability that you will win exactly 3 times? So what we did is we said, okay, we're playing 5 games. Okay, we want to win 3 times. How many different ways when we play 5 games can we have 3 wins? Well, we could go win, 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 loss, loss, win, loss, win, win, loss. I already lost track. Anyway, so we start out by counting how many that is, and that's the combinations of 5 choosing 3. Then we take our probability of success, which in this case, probability of winning is 25%. And we say we're going to win how many times? 3 times. And then we multiply by the probability we're going to lose. Probability that we're going to lose is 75%, and we're going to lose twice. Okay, so this is winning 3 times and losing 2 times, and this is how many different ways we can do that, and that's how we calculate that. Now remember that we used a standard normal curve to approximate probabilities. Like if I change this to be not exactly 3 times, but let's say less than or equal to 3 times. Okay, well, I could do winning 0 or 1 or 2 or 3 and add them all up. But remember how we used a normal distribution to approximate that. We said that the mean is the expected value, which was n times p. So in this case, 5 games times 25%. Okay, so 5 times 0.25. I don't know why I grabbed a calculator to do that. 1.25. We then calculated the standard deviation, which was n times p times q, okay, which would be the square root of 5 times 0.25 times 0.75. So that would be 5 times 0.25 times 0.75, about 0.97. Okay. And then we used our standard normal curve, right? We found the z-score. Now remember we had to do a continuity correction, right? So we, instead of 3, we'd go to 3.5 to make sure we had that entire bar. We'd find the z-score and we use our table to calculate that probability. And I don't know if you guys were wondering this, but it's like, why are we approximating a standard, a binomial probability using a standard normal curve when we could just do the work, right? In fact, our calculator can, right? Binom CDF allows us to do that. Excuse me. Well, we're going to see today why we use that standard normal curve to approximate it. Because what we're going to start doing now is saying, you know what? Instead of a situation where we know the probability of success and we calculate the likelihood of so many successes, what if we don't know the probability of success? Can we come up with a confidence interval? Let's say I play a game 10 times and I win 7. Does that mean the probability of success is 70%? Not necessarily. It could be 50% and I got lucky and I just won a couple more than was expected, right? So can we get a confidence interval? Could we say something like we're 90% confident that the probability of success is between 50% and 90%, or maybe 65% and 75%? A statement like that, right? So in the review problem that we just did, we knew the probability of success beforehand, and we found the probability of our successes if we had n trials. Now what we're going to do is we are going to say, if we have our successes out of n trials, what do we think the probability of success is? So remember, when we use a standard normal curve to approximate the binomial distribution, our criteria is that n times p has to be greater than 5 and n times q has to be greater than 5. Okay? This, remember, is the number of successes, n times p, and this is the number of failures. Okay? So number of successes has to be greater than 5, number of failures has to be greater than 5. Now, remember that when we are estimating a mean, estimating mu, okay, x bar is a point estimate for mu. Well, we need a point estimate for p, and we call that p hat. So just like x bar is a point estimate for mu, the point estimate for p we call p hat. We draw this little upward little symbol there, and we call it p hat. It's like p, the letter p is wearing a hat. Okay, p hat is our point estimate for p. Okay? So how do we calculate p hat? Well, we take the number of successes out of the number of trials. So, by the way, when we say n times p has to be greater than 5 and n times q has to be greater than 5, remember, we don't really know p and q. So I'm going to change this to say n times p hat has to be greater than 5 and n times q hat, the point estimate for likelihood of failure, has to be greater than 5 as well. So let's look at a problem here. Let's say a random sample of 188 books purchased at a bookstore. Okay, so we have that random feature. Okay, show that 66 of the books were mysteries. Estimate P, the probability of a book being purchased at the store being a mystery book. All right, so if I'm in the store and I randomly grab a book, okay, I want to know what's the probability that that book is mystery. So basically, what's the proportion of all the books that are mystery? We know 66 out of a random 188 were. Well, what is P hat? P hat is 66 out of 188. So P hat, oh, come on, pen. Is about 0.35. So we're estimating that 35% of the books are mystery. Okay? This is our point estimate for P. Okay? So how do we get to the point where we can make a confidence interval? So we can say we're 90%, 95, 99% confident that P is between this and this. Well, we have to be able to calculate a margin of error. Here's how we do it. Okay? We use the critical z-score. So depending on if it's 90, 95, 99%, we know those z-scores. Okay? Times the square root of pq over n. Notice n is underneath that square root. Okay? So we're back to z-scores because we're using standard normal curve and not t-distribution. And why are we using that? Well, remember that when we were estimating mu, our error formula was our z-score times the standard deviation divided by n, right? Remember that? Okay. Well, how do we calculate the standard deviation for a binomial probability? Remember when I did it on this page? It's the square root of npq. Okay? And if I change that standard deviation, that sigma, to the square root of n times p times q, and I put it over n, watch what happens. Well, notice all of this is under the square root. So if I'm going to put n under the square root, it needs to become n squared. Okay? And then we notice that this n cancels out one of those n's, and we have the critical z-score times the square root of pq divided by n. So it's the same thing as what we were doing before. It's the critical z-score times the standard deviation divided by the square root of n. But we've just simplified it. Instead of doing the square root of npq divided by n, we're just taking the square root of pq times n. N is under the square root. So that's how we calculate our error. To get our confidence interval, we take p hat minus the error and p hat plus our error. So let's go back to that problem and let's find a 95% confidence interval for the probability of a book being purchased as a mystery book. All right, so remember our p hat was 0.35. We are going for a 95% confidence interval, so we need to have the z-score for 95%, and that is 1.96. Now, if p hat's 0.35, what's q hat? 0.65. We also need to know how many trials there were. I believe there's 188. Yep. Okay. Now, before we go any further, oh, another sneeze coming. I'm sorry. We need to make sure our criteria is met. Is n times p hat greater than 5? Well, remember, this is just the number of successes. It was 66, wasn't it? 66 out of the 188. If I take 188 times 0.35, I'll get 66. Okay, and n times q hat, that's greater than 5, that's the number of failures. If 66 were mysteries, that leaves, what, 122 that weren't. We're well over our criteria, so making sure that's good. All right, error time. Critical z-score, 1.96, times the square root of n p q. And when I say pq, it's p hat and q hat. Oops. Over, I almost made that mistake, didn't I? Okay, I was going to go with the old formula. Okay. See, this is why we got to be careful, right? The square root, not of npq, of pq, 0.35 times 0.65 over n, which is 188. I almost did the long work, right? Square root of npq divided by n, but instead the square root of pq divided by n. So we get an error of about 0.07. Okay. So now we need to take our p hat minus the error and our p hat plus the error. We get 0.28 less than p to 0.42. So what does this mean? This means that we are 95% confident that the true probability of randomly purchasing a mystery book is between 28% and 42%. There we go. Let's look at another one. A survey of 100 students in a high school showed that 60% of students like school lunches. Okay. If the school has a total of 500 students, give a 95% confidence interval for the number of students in the high school who like school lunches. Okay. So we surveyed 100 of them. We've used this school lunch example many times, right? Okay. Instead of talking to, let's say, all 500 students, we do a survey of 100. We've gone through it. We've made sure that the survey, it doesn't have bias, all those type of things. 100 students, 60% like them. If the school has 500 students, what's a 95% confidence interval for the number of students who like high school lunches? All right, so what is our p hat? Well, 60% of 100 students. That's 60 out of 100.6, right? 60%. That means q hat is 40%. All right, okay. N is what? 100. Okay. Is n times p greater than 5? Do we have, if 60% of 100 more than 5? Yep. Is n times q hat greater than 5? Do we have, if 60% like school lunches, do over 5 of them not like? Yeah, that'd be 40 of them don't like it, so that's good. We're doing a 95% confidence interval. Okay, what's our z-score for 95% confidence interval? 1.96, isn't that the same one we did in the last one? Yeah. All right, looks good. Let's calculate our error. Z-score 1.96 times, I'm going to make sure I do this correctly, the square root of PQ, 0.6 times 0.4 over n, which is 100. So our error is 1.96 times the square root of 0.6 times 0.4 divided by 100. It's about 0.096, so about 0.1, about 10%. So we can take 0.6, our p hat, minus 0.1, and our 0.6 plus 0.1. So we get 0.5 to 0.7. Okay. Now, the question is, okay, not the probability, a confidence interval of probability, but for the number of students. So this corresponds to 50%, right? And that corresponds to 70%. So I would say I'm 95% confident that 50% to 70% of the high school students like school lunches. Okay? But how many students would that really be? Okay? Well, if it's 50% of 500 students, that'd be 250 students. So I'm going to make the statement here. So we're just changing percentages to number of students. Okay? We are 95% confident that 250 and then we have to do the 70%. What's 70% of 500? That would be 350 students like school lunches. So just that little extra step of converting the percentages to actually the number of students. 95% confident that 250 to 350 students like school lunches. That's cool. Neat that we're able to do that. Okay. So I'm going to switch it up here a little bit, okay, and say what's the what's the minimum sample size to have a maximum error? Okay? And we've already done this a little bit before, where we figure out, okay, what does n need to be? So if we had so in this problem, right, what is our error? Our error is 10%, or in this case, 10% of 500, it's 50 students. We can see that there's this total span of 100 students between the two. The error is 50%, or 50 students, okay, on either side of our estimate for P. But what if, okay, I wanted to survey enough students so that the margin of error was 25 students and not 50? All right? So how do we do that? Well, we want our error to be 25 students. Okay? So what is that as a percent? That's 25 out of 500. Right? So if I take 25 divided by 500, I get 0.05, or 5%. Right? Our error in this last one was 0.1, or 10%. Well, now we want our error to be 5%. So let's work backwards. Remember that error is the critical z-score times the square root of PQ divided by n. So if we're still with the 95%, it's still 1.96. Okay. P hat was 0.6. Q or Q hat was 0.4. But now we want to find n. Okay, that's what we want, and we want this error to equal what? 0.05. So let's solve this. I'm going to divide by 1.96. I'm not going to type that in my calculator yet because I don't want to start using a lot of rounded answers. What's 0.6 times 0.4? That's 0.24. Okay. I'm going to square both sides. So now I have 0.05 over 1.96. So 0.05 squared over 1.96 squared equals 0.24 over n. Cross multiplying and dividing, 1.96 squared times 0.24 over 0.05 squared. So just a little cross products action. I haven't typed in anything yet until now. 1.96 squared times 0.24 divided by 0.05 squared equals 368.8. Now, can I survey 0.8 of a student? No. So how many students do I have to survey to get my 95% confidence interval to be within 25 students? 369 students. That's how many I need. Okay. Now, if I were to go back through this again, okay, I would see that my error would be shrunk from 10% down to 5%. We'd be within 25 students. Interesting thing in this, the high school only had 500 students. If you're going to survey 369, you might as well try to survey all of them. Might not happen due to different issues that could come up, student absences, things like that. But if you have at least 369, your error is only going to be 25 students. All right? Okay. Now, in this one, notice, okay, we already knew P and Q, didn't we? That's because we already did the survey with 100 students. But what do we do if we don't already have an estimate for P and Q? So that's what we need to talk about next. Okay, so there's two different cases if you're going to find the minimum sample size. If you have a preliminary estimate for P, you can use that. Use the P and the Q, okay, and solve for N. Okay, just like what we did. We already had a survey with 100, so we had an estimate for P and Q. We worked on that. If you do not have a preliminary estimate for P, we haven't surveyed at all before. We have no idea what to expect. What we use is we use 1/4 for P times Q. Notice 1/4 is 0.25. Okay. Now, why do we use 1/4 times P times Q? What was P times Q in this last one? It was 0.6 times 0.4, which was 0.24. Okay, which is just a little bit under. Okay, and I want to make sure that I'm not being overconfident in my answer. Okay, so I want this number to always be smaller than maybe it could be. So notice 0.24 is smaller than 0.25. And what I did on this page is I looked at a lot of different possibilities, right? If P is 0.4, then Q is 0.6, and P times Q is 0.24. If P was 0.5, then Q would be 0.5, and P times Q would be 0.25. And notice as I increase P, I'm decreasing Q, and I look through all these scenarios. If P is 0.9, then Q is 0.1, P times Q is 0.09. Notice what's the biggest P times Q can be. If P times Q are really complements, the biggest that it can be is 0.25. Okay? So we're going to use the biggest possibility for P times Q if we don't have a preliminary estimate of 0.25. All right, so let's let P be a proportion of calls to people for which the caller reaches the person being called on the first try, right? So grab my phone and I call somebody. Okay. What's the probability that they answer on the first time, right? Because so often I call somebody, no answer. Got to call back again later, right? So if you have no preliminary estimate per P, how many people would be included in a random sample to be 80% sure that the estimate for P will be within 0.03? So we want our error to be 0.03. How many people do we have to sample? How many of these phone calls do we have to make? Okay, so 0.03. We want to find N. Okay. Now, we're doing an 80% confidence interval. We don't do those very often. What's a confidence interval for 80%? Well, that one is on my table, so I'm just looking on the tables in the back of the book at standard normal curve. 80% is on there at 1.28. Okay. Now, we have no idea what the proportion could really be. Is it 60%? Answer on the first time? Is it 40%, 30%, 90%? We don't know. So because we do not know, okay, we have no preliminary estimate for P, we're going to say P times Q is 0.25 because we know that's the biggest it could be. So here we go. Error equals critical z-score times the square root of PQ over N. Our error is 0.03. Our z-score is 1.28. P times Q, we're going to say, is 0.25 over N, and let's solve for N. Divide by 1.28. Square both sides. Oh, look at that stuff. So 0.03 squared over 1.28 squared equals 0.25 over N. Little cross products action, cross multiply and divide. N equals 0.25 times 1.28 squared over 0.03 squared. So we get N is about 455.1 repeating. So how many people should be included in our random sample? 456 people. Remember, we're always rounding up. If we round down, our error would actually be a little bit bigger than 0.03. All right, so that is how we do confidence intervals for our proportion P. Okay, that's how we find a minimum sample size if we are wanting a specific error for estimating P. Should be good to go. Thanks for watching. We'll see you later.